All right, thank you, Carly. So we're going to talk first about this quotient rule here. So um, we're recording and we're on number 1A for survey of calculus. So f of x equals 3x minus 4 over 2x plus 3. And we always want to imagine that there is a set of parentheses around this. And so this looks, roughly speaking, like the quotient rule that I was showing. So this is where it's something divided by something else. And we would want there to be, in order to justify using the quotient rule, we're going to see like a variable in both the numerator and in the denominator. If
Okay.
we if we don't see that, then there's easier ways we can deal with this rather than having to use the quotient rule. So if we only see the variable in the numerator, or if we only see the variable in the denominator, but it's a constant in the other, then we don't really need to use the quotient rule. So I'll give you an example of that later.
Okay.
But for this first one, so does your teacher use U and V or F and G?
Um, F and G.
F and G. Okay. So we'll call this F, we'll call this G. It's a little tricky because we have f of x equals, so
Oh, for substituting, he uses U
yeah.
and V.
Oh, he does. Okay.
Yeah.
So there are teachers that use f for the top and
Mm.
g for the bottom. So I do actually see that quite a lot too. But u and v is also common. So we'll go ahead and use that. And so we're going to define that. So u, of course, is 3x minus 4. We've got that. And then what's u prime?
3 minus. Um, it's 4. No. Can you run through how you do that again?
Sure. So we're going to take the derivative of each term individually. So the whenever you're
Oh,
taking
so
derivatives,
3.
right? Yeah. So that's going to be 3. The derivative of 3x is going to be 3. And then what's the derivative of negative 4?
4.
Well,
Well,
remember that what the derivative tells us is the slope. So
oh, okay.
if we had, remember the equation like y equals mx plus b?
Yeah.
So what's the slope? Where would we look to for the slope from that?
-4.
Well, m would be the
Oh,
slope
the slope. Sorry, a 3.
in the generic y equals mx plus b. So this is like the m, and so that's going to be the slope. If you had, let's say that it was just y equals a constant, so like just y equals negative 4. What would that look like if I tried to graph y
It would
equals
be a
negative 4?
downward slope.
Well, it would actually be not a downward slope. You're thinking downward because you see a negative there. So you're
Oh,
thinking that it's going to be
oh,
slope
I see.
downward.
It's upward through the -4 on
So
the.
we're going to go to negative 4 on the y-axis, and then
Okay.
it's just going to be a horizontal line that goes through negative 4
Oh, I see.
because it's saying that y
Because
is
it's just a
always
constant.
negative 4. It's just a constant, right?
Right.
And what's
Okay.
the slope? What's the slope of that constant?
0.
0. And so that's why,
Oh.
right,
Okay.
when we take the slope of a constant like negative 4, that's going to be just a 0. So
So
the
0. So just
yeah.
3.
Mm-hmm. So the u prime is 3 exactly, and then let's I'm gonna go ahead and get rid of all this stuff over here,
Okay.
and
Then I think I can do V. So V prime is 2 plus 0.
so v prime is 2 plus 0. Good. And so we actually
2.
don't even need to put the plus 0. So let's just
Okay.
simplify this down to we had 2x plus 3 equals the v, and v prime is just 2. All right, so now we're going to do the quotient rule.
Okay.
And do you recall what it is?
No.
Okay. I remember it is low D high minus high D low. So in other
That's
words,
the class I must have missed because that's everybody was saying high D low, low D high. I was like, what does that mean?
mhm. So it's the bottom times
Okay.
the derivative of the top. So the bottom was the 2x plus 3. So it's going to be 2x plus 3 times the derivative of the top. And what was the derivative of the top? What was u prime?
Um, uh, 3.
3. Yep. Minus high. So in other words, u,
Um, 3x minus 4.
3x minus 4,
And then, 2
and then
times 2.
2. Good.
Okay. So wait, how does it go? High V low, low V high?
Low d high minus
Yeah.
high d low.
Why do they say D?
Derivative of.
Ah, okay. Wait, that's quotient.
Hmm.
Low D high. Just want to write that down.
Hmm.
High. Okay.
And then on the bottom, we're going to have the denominator squared.
Okay. Over denominator squared. Okay. So 2x plus 3 squared.
Hmm.
Okay. So to simplify this, I want to break down the top first.
Let's go ahead and simplify that. Good plan.
Okay. So that gives me 6x plus 9 um minus 3x um plus 4.
Okay. Um,
So
we
I'm
we could
how do I
distribute the
do that?
negative there, but
The
I
two.
actually might find it easier to move the 2 out to
Oh,
the
okay.
front and multiply it by a -2, so we could
Oh,
like kind
okay.
of do it all at
That
once.
seems that makes more sense. Okay. So then minus 6x minus 8 over
So it's actually going to flip it to be a +8 because we got a negative times a negative.
Oh, right.
A way to check that is that notice how 3x minus 4 inside the parentheses, those are opposite signs, right? So the 3x and the minus 4, those are opposites.
Right.
After we distribute a negative, it flips both of them. And so if they started off as opposites, they should finish as opposites too. So
Oh, okay.
you see how the -6x, since that one's negative, this one now needs
Yeah.
to be positive.
Okay.
And then on the denominator, we're going to keep this the same for now.
Okay.
I think we may just leave it like this through the entire problem.
Okay. So now I want to combine my terms.
Hmm.
So 6x, so positive 6x minus 6x is just 0.
Good,
Um, so those cancel. And then plus 8, or sorry, plus 9 plus 8 is 17. So
good.
I have 17 over 2x plus 3 squared.
And that finishes it out. There's really not
Oh,
much.
really? Okay.
Yeah, yeah. There's not much else we can do with that. So
Not that
that
hard.
is the derivative.
Great. Okay.
Now, what if we wanted to take the derivative of this again? This is actually called the second derivative. I realize this is not what the instructor is requiring you to
Oh,
do.
but show me. That sounds interesting.
Yeah, but if you wanted to take the derivative, we can take the derivative as many times as we want.
Really?
And yeah, absolutely. Absolutely. There might not be anything there after a while, but you can keep on taking the derivative. And then so when we take the derivative again, this is one of those cases where it looks like maybe we could use the quotient rule because we have something on the top and something on the bottom. But you
Uh,
remember how I was saying that if you only have a variable in one or the other, you really don't need to do the quotient rule. And this is one of those cases where if we have 17 over 2x plus 3 squared, you've really only got the x in the denominator. So you don't
Right.
need to do the quotient rule. And we have a different approach that we could do. So I
Okay.
would I would bring this up to the top. I would make it a negative exponent in order to flip it up to the top so that it would become 17 times, and then this would be plus 2x plus 3 raised to the negative 2 power, uh,
Uh-huh.
because now that it's come up, it's going to be the opposite
Right.
power. And then I'm going to um, so this is actually not quite the second derivative yet. Let me hold off on that because all I've done right now is just change the algebraic representation of it. I haven't changed its value
Oh,
yet.
so when I write this, should I write F, like when I'm going down through my work,
Mhm.
should I write F prime?
Yeah, so this is actually how I would keep f prime. I would leave it like this. But when I'm setting it up to take the second derivative, that's when I would move it up to the top and make it a negative exponent.
Okay.
And then now that I have it as a negative exponent, here's where we get to practice the chain rule, which is what we need to practice this anyway for
Right.
this chapter. So good timing. So how does the chain rule work? Do you remember what
So
our process
it's
is?
the derivative of the outside times the inside the same. Um, and then uh times multiply by the derivative of the inside.
Okay. So I wouldn't necessarily say the derivative of the outside, but it kind of. So what I would say is we're going to apply kind of the general power rule where we're taking the exponent here, that negative
Huh.
2, and multiplying it times the 17. We're not going to take the derivative of the outside in the sense of taking the derivative of the 17. We're just going to leave it as a constant. But what we're going to do is we're going to multiply it by that negative 2. So this is going to
Okay.
become negative 34. And then this is 2x plus 3.
And then times 2.
We're going to have to subtract 1 from this when we
Oh,
take the derivative. So this is now going to be minus 3. And then it's going to be times a 2. Yeah,
yeah.
because we have to take the derivative of the inside, and indeed that derivative is a 2. So then this would be the second derivative. Now we've taken the second derivative. And that would be how you handle one of those fractions where there isn't a variable in both the numerator and the denominator,
Okay.
because we're able to just bring that denominator up, use the chain rule, and we're done.
Right. Okay.
And as you can see, that's pretty much just one step as opposed
Yeah.
to the
It's
uh
easy.
the it's easier. Yeah, it's easier to do the chain rule than the quotient rule a lot of the time. Not always, but a lot of the time. All right. So that was
A.
1A. And now for 1B, ooh, we've got natural log. Okay, so I'm going to scoot this down and we're going to work on a natural log. So y equals x cubed natural log x. All right. Any ideas on how to get started with this one? What kind of format does it seem like it could be?
Um, well, product.
Product, exactly.
Okay.
Because it's something times something else. And they both have x's in them.
Okay. So I want to put parentheses around those.
Yeah, you can. So this is U and V. We can use that same approach. So U and V,
Okay.
and we're going to
Can I
take the.
always use U and V?
Oh, sure, yeah, yeah. And in fact, there's a really powerful technique called U substitution that we're going to have a lot of fun with later. So U is equal to x cubed, and U prime is equal to, and then so we're going to want to take that 3, bring it down, and that's going to be 3x, subtract 1 from it. So
To the 2.
squared. Mm-hmm.
Yep,
And then,
sorry.
okay, so I did the easy one. Now you can do the natural log.
Oh, I don't even know where to start with the natural log.
All right, so the natural log,
You taking pity of me?
the natural log is going to be, um, it's kind of a special case. The derivative of the natural log is going to be,
Isn't it
uh,
10?
so
Like natural
the
log equals 10?
it's actually log equals 10. So if you just see log by itself, the base of it is 10. So for
Okay.
example, for what this means is 10 raised to what power has to equal that argument. So if x was like, let's say 100, let's say let's say we had something like that. So it was just a regular log base 10. The answer to this would be 2. And the reason why is because 10 raised to the second power is what gives you that argument of
I
100.
see. Okay.
And the natural log is simply, instead of that being a, um, instead of this being a 10, it is a 2.71, blah, blah, blah,
Oh,
blah. It's that number E. It's
yeah, yeah.
Euler's constant. So that's what natural log means. So it's the natural log of x. And the way that we handle those, it's a little different. What we do is we take the derivative of the argument. So this argument of x, what's the derivative of it?
0 or 1?
1. The derivative of x is going to be 1 divided by the original of it. So it's going to be 1 over x. That's how we handle natural logs.
Oh, okay. So what if would it ever say like ln 5?
So if it said ln5, that's actually a constant because you could plug that into your calculator and you would get a decimal answer.
Okay, so then that I would plug that into my calculator.
Well, it would be a constant, and the derivative of any constant is
0?
0. So its
Okay.
derivative would simply be 0. But if it has a variable in it, then, well, like, so let's say, for example, what if you have ln 5x?
I just have x. No, I have 0 times x, which is 0 times 1, which is 0.
You have the derivative of 5x as the numerator. So the derivative
Right.
of 5x, in the same way as, recall earlier that we had the derivative of 3x and that was just 3. The derivative of 5x is going to be just 5.
Oh,
So,
okay.
so in the numerator, we would have 5. And then in the denominator, we have 5x because that's the original. The
Okay.
fives cancel out, and we end up with just 1 over x. So the
So it's
derivative of
always going to be 1 over x.
it ends up as 1 over x. Yeah. Yeah.
Okay.
Yeah.
So whenever it says ln and I'm taking the derivative of that ln is 1 over x.
Yes. Although
You're
I
gonna have
can,
situations.
yeah, I feel
Sure.
like I can come up with some other scenarios, but
Okay.
for now,
Okay.
we're on a good path if you can remember to take the derivative for the top and the original for the bottom.
Okay.
All right, so I'm gonna leave those um, like that. Okay, so now we've got everything, and what we need to do is just apply the rule.
Low D high, high D low.
That's for the quotient, but are we doing the quotient?
No, we're doing the product.
Product. What's the product rule?
I don't know.
So it's they just kind of like multiply this way.
Okay.
So you get the u, which was, here, let me get rid of this stuff for the derivative. So you have the u, which is x cubed times, and then the v prime, which is 1 over x, plus, it's going to be a plus sign instead of a minus sign.
Okay.
So when it's a product rule, it's a plus. And then it's going to be the u prime, which is the 3x squared,
So, okay, it's the u times the v. Well,
U times U
times
times the V prime. And then U prime times the V. So
okay,
there's
and it
always
doesn't matter which order. Like, let's say
it
I do
doesn't
v
matter.
times.
No.
Okay,
Yeah, it
u
doesn't matter.
times v, and then I just want to make sure I write all this down. U prime, hmm, u prime times v, v
hmm
prime times u.
hmm
Okay,
Yeah,
okay,
as long as one of them is the derivative and the other is not, and then you switch and do it the other way.
okay. And this is we're starting now. I can write y prime equals.
That's right. This is Y
Okay.
prime.
So
And
how would one even consider starting to simplify this?
think of this as being x cubed over 1 because you can always turn any number into a fraction
Okay.
by dividing it by 1, right? And so that's what we just did there. So now we've got x cubed on the top and x to the first on the bottom. Think of
Oh,
that as
okay.
x to the first. So
So we
how
have x cubed over x.
x cubed over x, and how can that simplify?
To x squared.
X squared. So that first one is x squared. And then as far as what we can do with the next one, the answer to that is nothing. And so we're just
Oh,
going to leave
okay.
this as 3x squared ln x.
Oh, you mean cubed? Isn't that cubed? Oh no, it was squared. You're right.
Yeah, it was squared because when we took the derivative, it lost one of the degrees.
Right. Okay. So that's it. That's all we can do.
Yep, we're good with that. So that is our answer for that one.
Okay.
All right. And then the next one, this is going to require us to do quotient rule and chain rule, I think. Yeah, let's see. Let's see how this goes.
Yeah, quotient because of the fraction. Okay. But then why would you think that we would also need the chain rule?
Actually, we don't. I was I was looking at it kind of
Okay, I was trying to understand where your mind
gla-
was.
yeah, no, I was just sort of glancing over that. I actually don't think we're going to need to use that. So this is not going to be as crazy as it looked.
But I still need U and V.
Yeah, we can do this as the U and this is the V.
Okay. So U equals 3 ln x. So because it's not ln 3x, it's 3 times ln, so it's 3 times 0. So it's just, but it's still 0.
Well, remember that the derivative of ln x is not going to be 0. What was the derivative of ln x?
Um, oh, 1 over x
1 over x. Good.
equals 3 times 1 over x. So 3 over 1 times 1 over x. So we get 3 over x.
3 over x. Yeah, that's good.
U prime equals 3 over x. Okay, let's look at v. V equals 1 plus x squared. So v prime equals, how did we say we dealt with? I don't know if we said how we dealt with squares. Oh no,
So
we
it's
um it's the 2x to the 1, so just 2x.
2x. Good.
So 1 plus 2x.
hmm
Okay, I'm getting the hang of that. I wouldn't have been able to do that. Well, I wasn't able to do that when we started, so. Okay. This is good. I might pass.
I think so. I think so.
I just have to
Um,
like ingrain I have to like remember the rules and what to use. It was helpful when you wrote out the like I mean I took notes on it, but like when you did the like this when it's something times something
mhm.
product, something over something quotient, because then I can like see it. And now I just have to practice looking and then without looking at my notes, identifying which
Ab- Absolutely. Yep.
but that was so much help like that was so helpful when you like put it like that because It's easier when you're like, it's just something times something equals.
Right, right.
It's like
It's
when they're
much
like,
harder to get intimidated by it. Yeah,
right. Like something times something versus something over something versus something to something.
right.
It's
That's
just a
it.
bunch of something somethings.
That's all it is. That's all it is. Yeah. Which pattern of some things are we looking at?
Right.
So we've got now the quotient rule to apply. And do you recall what that formula was?
Um, that was low D high D low over denominator squared. Okay.
Hmm.
So that is low 1 plus x squared parentheses low derivative, so derivative of u, so low d high, yeah, wait, low, no, derivative of high, so derivative of u,
Hmm.
which was 3 over x.
Hmm.
Okay. And parentheses high 3l and x d low derivative v, which was 1 plus 2x. Okay. That was not that bad. Okay, over. Oh wait, I forgot. Over the denominator squared. So 1 plus x squared squared.
Perfect.
Okay. I think I'm getting the hang of it.
So
Now to
you put it
learn how
you
to.
put a minus there for the top, right? So it was
Oh, wait, what?
because it sounded like you said parentheses, but I just wanted to make sure that we have the same thing before we
Oh,
go any further.
minus?
Yeah. So
Wait.
it's low. Remember that it's low D high minus high D low.
Oh, wait, why is there not, why is it just 2x? What happened to the 1?
Well, what's the derivative of one?
Oh, is it 0?
Hmm.
I did not know that. Okay. Um, minus. I did not say minus. I just wrote times. Okay. Minus parentheses 3 ln x times 2x. Okay. I think we're on the same page now. Okay.
Cool. Okay.
Um, so I want to simplify the top first. Um, what's the easiest way to be multiplying that whole thing by 3 over x? Because I look at that and my brain just gets upset.
Hmm. Hmm.
Would it be to put the 1 plus x squared over 1?
You could do that. Yeah.
Okay.
So let's take this and we'll put it over one.
Okay. That gives me 3 plus 3x squared over x, right?
Gotcha. Okay. Over
Okay.
X. I'm with you. Hmm.
Okay. So yeah, so that helps simplify. So just the like thought of like putting it over 1 helped me
Hmm.
like clear what I was doing. Okay.
Cool.
Um minus um hmm. Is that so does the 2 multiply the 3?
Yeah, actually it can because
Okay.
those are both outside of the natural log there. So yeah, we could do that. So that would
Okay.
be
So minus
6x.
6 ln x squared.
Well, no, that part. So the lnx is going to be the argument of that is the x.
Ah,
So
is
you see
separate.
how I like put it in a little box. Kind of
Yeah.
think of that as its own
I saw
thing.
you were doing that earlier too. Okay.
Yeah. And then so the 2x multiplies times the 3, that's okay. And that'll give you a 6x outside of the natural log. That's not part of the argument of
Right.
the log. So
Okay.
it's gonna be that over, and you can think of it as being over one. And then
Okay.
this is being now still divided by one plus x. squared
Oh,
squared.
I wrote plus 1x. That's not gonna work. Okay. 1 plus x squared squared. Okay. Um, I'm not quite sure where to go from here because you can't exactly subtract these from each other. At least not how they are.
True, true. So what you could do is get the same common denominator, just focused
Okay.
on the numerator. So kind of zoom in and pretend this is our whole world right here. And we're not worried about the rest of what's going on. We're just focused on this. We could get the same common denominator by multiplying the second term by x over x. And that gets us to have the same common denominator. So yeah, this is x on the bottom and this is x on the bottom. Now we can combine those together as one.
Okay.
Because I'm allowed to multiply this denominator by x as long as I also multiply the numerator by x too.
So that gives me g prime equals 3 plus 3x squared over x minus, is that 6x squared ln x squared?
Right.
Okay.
What, or did you say ln x or ln x squared?
I said ln x squared.
It would actually only be ln x
So
because
does nothing affect that x at the end?
yeah, not really.
Oh, okay. I didn't know
It
that.
takes a lot to mess with that x.
Okay, so
Um,
you just don't touch that x. Okay.
yeah, yeah.
Over 1 plus x squared squared. Okay. You still can't subtract them.
No, you can't. You can't. What you
So
can
I don't know
do
what the
though,
point of that was.
well, now we're going to use the keep change flip. Do you remember that the rule for that?
I don't know if I have room on here for the keep change flip, whatever that means.
So what I'm going to do is I'm going to make this an even uglier fraction than it already is by putting a 1 down here. And so now I've got a fraction, and I'm going to put that in green over here. So I've got a fraction on the top, and I've got a fraction on the bottom. So I've got like a double decker fraction going on here. And when we have those, we can use the keep change flip approach. So I'm going to keep this top. I'm going to change this division into multiplication, and I'm going to flip this denominator. So that's going to be the plan. So I'm going to keep, like I said, I'm going to go ahead and keep this 3. Ooh,
I
let me try
gotta
that
see
again.
how you do this.
Yeah, so it's going to be 3 plus, oh, I meant to change the color. I wanted black here. Okay, so this is 3 plus 3x squared minus
Green, I guess, is 3.
x squared ln x divided by x. So far, so good, right? That's the
Right.
keep. That's the keep. Hasn't changed anything on that. Now the change is going to be multiplication instead of division. And the flip is going to be, I'm going to take these and reverse them. So the 1 is going to go on the top now, and 1 plus x squared
So I
squared.
don't know that I would be able to do that on my own. Okay, wait. Hold on.
Mhm.
You always keep the top?
Yeah, the top stays as it is. Mhm.
Okay. Keep top.
Mhm.
What do
Change
you mean
it
by
from division. Yeah, change it from division to multiplication. And
okay.
to do that, you flip the bottom.
Okay. So by change you mean flip. So it's a keep, change, flip is like one movement.
Yeah, because it becomes, instead of division with this denominator, it's multiplication with the reciprocal.
Okay. That makes sense. Okay.
And then so now we're pretty much done because
That's
it's
it?
just that's it. There's nothing else we can do with this. We've got it as a single fraction. So
Thank
it was
goodness.
Yeah, it was a lot of fractions within fractions, and now it's all everything is um, simplified down to the point where it's just this mess on the top divided by this mess on the bottom. And that would be our answer.
Oh, I see. X. Because we multiplied the X. Okay. That's a process.
That is a process. Yeah. So this was not an easy problem. This was, it didn't necessarily require the chain rule, but it did require a lot of algebra. So we started with this quotient rule.
Yeah.
We applied the quotient rule, and then it took a lot of algebra to get it out of a fraction over a fraction over a fraction. So yeah, we got it out of that and simplified it down to the, well, simplified, right? It's still pretty much a mess, but
Yeah.
that is what our
I like
derivative.
how in math you get to a certain point where you're like, it's a mess, but it's still a mess. So but it's somebody else's mess now. We just beat.
Right, that's exactly it. Somebody else's mess now.
So funny.
So
Even
our
mathematicians give up. They're like, the math,
done.
it's just a mess.
It's a mess. Yep. Yep. That's as far as we're going with it. So we're on D now,
Yes.
and D
How
has,
much is D gonna take? Because
yeah, that's got more logarithms in there. So this one's h of x, and what rule does this look like to you? Just from
um
first glance.
that looks like the product rule.
I agree. Yeah, we could
Okay.
handle this as a product rule for sure. All right, so this is going to be my U and V situation again.
Times x squared minus ln x. Okay.
And I'm going to write the U not as the square root of x, but I'm going to write it as x to the 1/2 power to make it
Okay.
easier to find the U prime.
Okay. U equals x to the 1/2. Is that not finding the prime of it?
So we haven't found the prime yet. We've only rearranged the way this looks because this is an understood 2 here, and this is an understood 1. And the numerator and denominator come from those understood numbers.
Okay.
But again, that's just an algebraic rearrangement. That's not a
Sure.
that's not a derivative yet. Mhm.
Okay. I'm gonna be honest, I have no idea how to take the derivative of that.
We're going to do the same thing that we've been doing with the general power rule, where we take
Oh,
this.
so 1/2, it's like 1/2 x.
Good. 1/2 x to what power?
Um, to the half.
Well, I actually
Well,
have to
people, I hear them say -1/2.
that's right. I have to
Okay.
subtract one. And if I can't really combine those yet because they don't have the same common denominator. So what I'm going to do to get the same common denominator is multiply this by 2/2. And when I do that, see how now they've got the same common denominator, but it's 1 minus 2. That's where I get a minus 1/2 from.
Uh, okay.
And you don't really notice this yet, but technically what we're doing is we're taking the inside, the derivative of this inside as well.
Yeah.
And that is dx with respect to x. So that's going to be dx. But anytime that we have the same thing on the top and the bottom, they do cancel out. And so we never notice that that's there, that we're taking the derivative of x all along, because
Yeah.
it's the derivative of x is simply 1. So we sort of ignore it, but that even in the general power rule, that process, the chain rule process is still happening.
Okay.
All right. And then the um, V, what do we get for the V?
V equals x squared minus ln x. V equals 2x minus 0.
Is the derivative of natural log 0
Oh, no, it's 1
over?
over x. Okay. Okay.
So now the product rule requires us to do what?
U prime times V, and then V prime times U. So U prime is 1 half. Okay, wait. So I say H prime equals 1/2 x to the negative 1/2 um times so put that in parentheses. Okay. Um thought so. Okay. Times V, which is 2x minus oh no, that's V prime, sorry. V, which is x squared minus ln x. Okay. And then is it minus or plus?
It's always plus for the product rule, plus for product,
Minus for
and
quotient.
minus for quotient.
Let me write that. I don't think I have that in my notes. Okay. Minus. Okay. Minus V prime, which is 2x. Oh no, plus. We just went over that. Okay. Plus 2x minus 1 over x times V, which is no, times U. My U's and V's look the same in my notes. I have to like put little tails on them because that's gonna get confusing. Okay. It's taking me a very long time. Okay. Times U, which is the square root of x.
Right.
Okay, we got there.
Cool.
Now we need to simplify this. Hmm.
So it's a mess as well, right?
So,
A lot of these are messes, right? Um, what I would probably expect to see is factoring out the fraction, the 1/2,
okay.
and factoring out the x to the negative 1/2.
Um, I'm just trying to process where you got that from. 1/2 x to that. Oh, okay.
So I'm actually just going to factor this
How does that
whole.
how does that factor how does that work with everything else?
So we're dividing this out of this first term.
Right. Oh, okay, not out of the okay. Okay. One.
And then we're also going to divide it out of this term as well.
Oh, okay. So, but how did you know that you could do that?
So what I'm factoring out is the smaller of the exponents, where I see over here a negative x to the 1/2, or x to the negative 1/2 rather. And I
Uh,
see over here x to the positive 1/2. And the smaller of those two is the negative one. So that's what I'm going to factor out.
okay.
And then when I divide this, remember that if the
Oh, I have to divide them all
yeah, so you're dividing this, and you
by
can
one half.
apply that keep change flip approach. Which before I do it, what I'm going to do is rewrite this as um, the x coming down to the bottom and becoming x to the 1/2 on the bottom because it was a negative, right? It was x to the negative 1/2. I'm going to put
Wait.
it down.
uh, Oh, you rewrote it. I was
Yeah.
like, so okay, wait. So that's from the -1 over x.
Yeah. So that x to the -1/2. And I'm putting it down to the bottom of that little fraction.
I'm a little lost. Okay. Um.
Yeah. So let me back up. Remember that I'm and I'll put the parentheses back here because I kind of lost those parentheses when I erased. So this is like that. So remember that I'm dividing. Let me say that again. That I'm dividing this by 1/2.
Oh, I see. You changed the Okay, that's where I was getting lost. You changed the square root of x to x to the 1/2.
Right. Right.
Okay, I was trying to figure out why mine didn't match yours.
Mm-hmm. Yeah. So I'm leaving that as a x to the -1/2, but then I'm going to bring it down to the bottom to make that exponent positive. Because if you have x to the -1, that equals 1 over positive x to the 1, right? Because you can move things by changing the exponent, by changing the sign. And
Yeah.
so if I had x, let's say to the -1/2, what that means is it comes down to the bottom and it's going to be a positive 1/2 on the bottom.
Okay. Okay.
So that's what I had down there for that denominator.
Ooh, not pretty.
No, no.
My brain is much better though than it was.
That's yeah, it's a lot to
It must
track.
have been
So
it must have been in me for a while.
it's hard to do math when you're sick
Yeah.
and your brain is foggy for sure.
Yeah.
Um
Glad that because I thought it was just me, but but it must have just been
well,
sick.
this is genuinely hard too.
Yeah.
Yeah, so when I'm dividing now by the 1/2x to the 1/2, keep in mind that keep change flip thing. So when I multiply by this, so I'm doing a keep change flip thing, and so this becomes
So we're multiplying, okay. We're multiplying the second part by 1/2x to the one
well
half.
when we make it multiplication, we're gonna have to flip that. So the one will end up on the bottom, and the top is gonna have the 2x to the 1/2. Because see how it was 1/2x to the 1/2. I flip that when I make it multiplication instead of division.
Okay.
So
I'm
this
gonna
is
look back at this and study it.
yeah. So I'll actually send you the recording of this, and
Okay,
you can yeah, you can follow along that way. So
okay, great.
yeah, that should hopefully help. So that's going to be like this, and then so here's the nice thing is that when you've got an x to the 1/2 and you've got an x to the 1/2, when you multiply and they have the same base, what can you do with the exponents?
Um, just combine them.
Combine them, and
So
so
I
when you
get one.
add those together and you get 1 exactly. So that comes out to be a 1. So it's x to the first, and then there's a 2 there, right? So that
Right.
2 multiplies. And so that was these two parentheses multiplying together. We still have this one over here. And so actually we can multiply. We could here, let me simplify this a little bit. So this is what we're factoring out. And I'm going to leave this off to the side because we're pretty much done with this part. And then what's going to be in the parentheses is the leftovers. So this is going to be gone. And we're going to have x squared minus ln x and then we're gonna have a plus. And let's talk about what happened here. So we just said that this reduced to 2x to the first power, right? Because the 1/2 added with the 1/2 equal to 1. And we don't really have to write that, so we can just leave it like 2x. And then this was 2x minus, and this was 1/x. So when I distribute that 2x, what's 2x times 2x going to give me?
4x.
4x. Remember that it's 1 and 1, so it's 4x squared.
Uh-huh.
Because it
Okay,
was 2x times 2x is
that next
4x squared. Yep. And
2x.
then 2x times the 1/x, what's that going to give us?
Um, that's gonna give us 2x over x.
And can that simplify?
Um, yes. Um, 2x over x is like 1/2 x. No. Wait. 2x over x is just x. 2. 2. We're getting rid of the x's, obviously.
So we've got our -2 there. And I could actually get rid of these brackets. I don't really need these. These are nothing's acting on it, so I can get rid of those. And that makes it so that I can combine like terms here. So you see how there's an x squared that could combine with the 4x squared. Let me scoot down a little further.
Okay, wait. How did you get 4? Oh, it's because 2x times 2x is x squared. Okay. Um, okay. So then we get 5x squared.
Mm-hmm.
So I still have the h prime equals 1/2 x to the 1 - 1/2, and then parentheses 5x squared. We can't combine the negative. We can't do anything with the negative ln x or the -2.
Good. We just bring those down.
But we can do we have to multiply the 1/2 x to the.
I'm going to leave it like that. I'm going to leave it factored like this.
Okay.
And I'm going to say that's another mathematician's problem to deal with.
Beautiful.
All right. So I'll go ahead and end the recording here, and we'll pick up again